So here's a big theorem. If we have linear space in a subset, and let's suppose the 0 is in W, is in the subset. Also, that the subset is closed under addition and closed under scalar multiplication. Then W is a subspace. Well, what do we need to show? I'm actually probably not going to write anything for this because we've done all the work already. A subspace, we can look at a definition here. If W fulfills the definition of linear space with the same addition and the same scalar multiplication, then W is a subspace. So we need to show that W is a linear space in its own right. So what do we know? We know the 0 element is in there, and we know that it's closed under scalar multiplication. So I need to show, it's the last scrolling, sorry about that. So I know that's closed under addition. That's by assumption. X plus y is an element of W now I'm checking. I know it's closed under scalar multiplication. By assumption, those are the first two things. And 5 also holds. So I'm assuming 1 and 2 and 5 here in the statement of the theorem. 3, 4, 7, 8, 9, and 10 are all just consequences of the fact that we've got this little set W and it lives inside V. But it's true for all, 3 is true for all elements of V. So it's got to be true for elements of W, because since every element of W is an element of V. Similarly with that, if it's true for everything in V and W is in V, that means it's going to be true in W. Same thing there, same thing there, same thing there, same thing there. The only thing that we have is we don't have 6 yet. I need to show you 6. So 1, 2, and 5 are by assumption. 3, 4, 7, 8, 9, 10 are all true of any subset, not just ones that are closed under addition, scalar multiplication, and the 0 elements are in there. So I only need to show you additive inverses, but I can do that because we already proved it. That's here. If you assume that it's closed under scalar multiplication, we're trying to prove 45 here. It is closed under scalar multiplication here. So if it's closed under scalar multiplication, if x is in W, then the additive inverse of x is also in W. So really, this theorem just kind of collects together a whole bunch of ideas that we've already seen. And so what this does, most importantly, is this gives us a very easy way of checking to see whether something is a subspace. Instead of checking 10 axioms, we're just going to check 3. Is 0 in it? Is it closed under addition? Closed under scalar multiplication?